not supposed to talk today, honestly, till the last week, basically. So Santosh and Sumali, who is the member of the scientific committee, we have some unwritten rules. So we do not invite ourselves to give talks in this point, but we invite ourselves to give some tutorials. That's how. But tutorial is supposed to not necessarily talk about your own work only, but to somehow broaden. All right, so Santosh wanted to talk about the entropic lattice Boltzmann, but this certainly very heavy subject, so he managed to fraction his leg through that, supposedly, and the doctors advised him not to fly. So who is going to replace Santosh? Certainly the former scientific advisor. You have to. So that's why I'm here today, and I will talk a little bit about some stories under the title of Asymptotic Freedom, which is actually indeed about drawing some attention to that subject, to the lattice Boltzmann. Once again, maybe from a slightly different standpoint. So this work was done, and we were entertaining each other with Ali over the last year. So the paper with that title actually is going to appear, I think, this month in PhysRef. All right, so I shall talk about lattices, symmetries, and Galilean invariants. I will talk about equilibrium. So we are moving to lattice Boltzmann, and then there is a question: what is the equilibrium in certain way? And the focus of this work is about existence of lattice Boltzmann. So what are the necessary conditions for it to exist as a numerical scheme? And we will answer this question in some way by showing the necessary and sufficient conditions for that. And some sufficient conditions for nonlinear stability will be also mentioned. That was probably what I think Santosh would be doing if he would be here. Okay, so it's a tutorial. I will set up the lattice Boltzmann once here. So what's that's a little dot. Okay. So we consider standard discrete velocities, and they are constructed this way on the plane for the demonstration. So we take the coordinate system literally like that, x and y, and three velocities in x direction, as shown, right movers, left movers, and non-movers in the middle. So in the y direction, we choose the same three velocities vertically and make a tensor product out of this 1D velocities to get the 2D velocity set. So this is the standard D2Q9 velocity cell. So to these velocities, we associate the discrete distribution function, or populations, as we used to call it. And here I number them with the two numbers, well, self-explainingly, the x and y directions fixed in this notation. So these are populations. Now, important to mention already here that this is the lattice Boltzmann viewpoint on the matter. So by choosing this set of velocities, we actually have chosen a fixed reference frame. And fixed reference frame to choose is something already a bit contradictory to the notion of Galilean invariance. So we will suffer at some point about that. But not yet. So what is lattice? Lattice is the blessing of the method, really the blessing of the method. So, and it can be said in a very short sentence. If you have a grid point, and if you step in any direction according to the velocity set, you will meet another grid point. So that leads to the exact propagation in space. Now, so to show it in picture, I will pave the plane with these velocity cells with a little offset so that you see the vectors. And this is the propagation. So copy and paste operation from the velocity to the next same velocity at the next grid point. So 3 times to show is enough for everybody to understand what's going on in the propagation. Now, collision or relaxation. So we consider conserved quantities, so the nodal averages of the populations. So the density and the momentum, and now the relaxation is going to the equilibrium in some way. So the most important step now remaining is to set up the equilibrium in the lattice. Okay, so I will consider a generic class of equilibrium and start with some basic construction. So again, 3 velocities in x direction, and I have 3 equations for 3 unknowns, density, momentum, and pressure like, so written in all the details for the 3 velocities shown. I can solve this 3-by-3 system, and that's now the solution in terms of the momentum-like variable and pressure-like variable. Going to the 2D, the same way as I constructed the velocities by tensor product, I construct the products of these base elements to get the family of populations. So these are pre-populations. It will be a placeholder to construct equilibria. So there are 6 parametric, and the parameters for each entry are the sort of velocity-like variable, theta, and the diagonal element of the pressure tensor. So all the construction will be to fill out these entries. Now, equilibrium, most commonly considered, is the Maxwell, so I can call it Maxwell's version of the equilibrium. What I mean? So what we need is the reference temperature, 1/3, and this is already directly related to the limited Galilean invariance of the system, because a cube of any component of the velocity, x, y, or z in this case, is the cube of that is the velocity itself. -1 cube is -1, 0 cube is 0, and 1 cube is 1. So that's a restriction. That means the diagonal elements of the third order tensor are hardwired into the system that just, again, conservation laws. So this is kind of a physical limitation here. But so the construction of Maxwell equilibrium looks very simple. So you assign the components of the velocity to the velocity-like variable in this product, and the pressure, the diagonal of the pressure tensor. Well, seemingly nobody will dispute that. So this is the reference temperature and the velocity square component. So like in the earlier. However, there is another version of the equilibrium, which I would call the Boltzmann. And that is one which minimizes the entropy function. And you can see that the difference to the Maxwell is, so Maxwell does not, so the previous Maxwell does not extremize any entropy function by itself. This does. And as you see, there is a more complex expression for the pressure component. So otherwise, the construction is just the same. So while they are different, if we expand both any of them, Maxwell or Boltzmann, till the so-called isotropic order, quadratic order, they match So they are same. So in that sense, they are kind of equivalent in terms of accuracy. So that means we will be able to recover the Navier-Stokes equation with this system in the limit of small velocities, much smaller than the speed of sound, which is the square root of the reference temperature. And these are the weights in front of that. So with this, you have already set up the lattice-Boltzmann equation in the following way. So I'll write it in the way which I like most to stress, well, for the next demonstration. But the propagation is on the left. That's in the units of time. So the time step is 1, conventional, convenient lattice unit, so-called. And the right is the post-collision, which is the convex combination with the parameter beta, which is on the between 0 and 1, between the current population and so-called mirror state. So this mirror state, in the most prominent version of the method, the lattice Vatnagar-Gross-Krug, or LBGK, is this. So if you will put it back, you will get the more familiar form of that expression. So, okay, so far so good. There is an asymptotic analysis which shows that for low Mach numbers, this recovers Navier-Stokes equation. I will come to that in a moment. With this Navier-Stokes equation, the kinematic viscosity is dependent on the only parameter beta in that expression. And of course, we are interested mostly in low viscosity, so that this beta should be as close as possible to 1, and this explains the notion of over-relaxation. So if this close to the value 1, the population starting here should over-jump the equilibrium and land closer to the mirror state. So how close? The interesting simulations start with 0.999, let's say. So between 0.999 and 1 at fixed grid, you have all the Reynolds from small to infinity. So because theoretically, so you have written that. But then you have to ask yourself a question, whether that system exists at all. What do I mean, exists at all? Whether it is stable, whether that will be stable. So what about stability? And indeed, stability was the, or is even still one of the major lines of research in lattice. So we will be specifically concerned with linear stability, and the question is whether this system is unconditionally linearly stable. So here is the collection of several lattice-Boltzmann realizations. I specifically talked about the LBGK, but there are other so-called multi-relaxation time. I will speak a little bit later about that. But now, for the time being, I'm just taking some empirical notion for that. And you can study the linear stability near the equilibrium point. So the classical step. And what you'll see will be actually rather interesting. That was observed by several people, including Ali in his thesis, I think, and some others. But so what you see is that we would like to have unconditional stability. So the velocity component computable by the lattice-Boltzmann is between -1 and +1. So the size of the link in the velocity. So then we see that whatever method or whatever realization you take or you see, depending on the velocity, the stability domain, so there is no stable realization above certain value of the velocity, 0.42. So, and the other observation is that when the viscosity goes down, the stability domain always shrinks. This way of shrinking is different for different realizations, as you might see, but all of them do that, shrinking. So none of them, therefore, is unconditionally stable. And I'm talking about the realization with the most common Maxwell distribution, the one which I mentioned before. So what is 0.42? Well, when we evaluated this number, I realized that 42, of course, is the answer to the ultimate question of life, the universe, and everything, computed by the deep thought computer in the novel The Hitchhiker's Guide to the Galaxy by Douglas Adams. But as you remember, this book, they got the question, the answer, but they didn't know the question. So let's try to understand what is the question. And let's play a certain game. So let's not assume. So we, as an example, I assumed the Maxwell distribution with the idea of isotropic pressure. The pressure does not depend on the velocity, which is, of course, so for the Boltzmann equation, and was known to Aristotle, I think, well, to Archimedes himself, that the pressure, well, certainly to the Blaise Pascal in any event, so that the pressure in any direction is the same and does not depend on the velocity with which the fluid is moving. But remember, we are not fully Galilean invariant. So we have to assume, not to assume anything, we have to start by allowing, in principle, the pressure to depend on the velocity. And find whether or which solutions to the pressure give us stability in the system. A very legitimate question. And you see, I'm not supposing anything. I'm just, if the answer is isotropic pressure, beautiful. If the answer is something else, well, we have to look at it and understand what it means. Okay, so we are playing some kind of renormalization group strategy. That means we have a field of theories parameterized by the pressure, which is now not yet known. And we do the coarse graining, the conventional hydrodynamic limit, look at the special parameterization with modes, and consider the stability of these modes. And that will be some necessary conditions for stability. So it is actually possible to do the evaluation in one dimension. Why? Because we are thinking about the necessary condition in the first place, and the same perturbations, same response will be also available in the multi-dimension. So it will stay in the system, whatever dimension we consider. So, and that's for analysis. So we do the coarse graining, the Chapman and Skog method. I do not go into these details. Write on the lowest order approximation, the Euler type approximation, Euler type system, we get we need to do the characteristic analysis, which is in this case very simple, solving for the quadratic equation. And we also, as you see, keep the dependence of the pressure on the velocity not yet defined. So we, in principle, can think about the velocity dependence in some way. So these are two traveling modes, and that's the speed. These are and the convention is a positive square. So this mode analysis rewrites the earlier level conservation law in terms of two coupled wave equations. So just to stress what these modes are doing. So these are normal propagating modes in the system. The next step is the Navier-Stokes level. And here we have a correction through the non-equilibrium pressure tensor written here out. And it contains two terms, two quite different terms. The first, with this capital A, is a viscosity factor, and because it's multiplying the gradient of velocity, and that is expression in terms of the modes. Convenient. And there is a compressibility error, absolutely undesirable term, which is written here in terms of the pressure, the derivative of pressure with respect to velocity, which we do not know yet, and the velocity itself. Okay. Now, the necessary condition of stability. We take that system on two orders and consider the usual linear stability of these hydrodynamic equations. So as you can see, this is the dispersion dissipation relation. And what is important, we find out quite generally the attenuation rate of the modes in terms, written in terms of the speeds of the modes. The necessary condition of stability is that this dissipation relation is actually correctly dissipating. So the positivity of both the rates. So we can plot. That's why it is convenient to do the analysis in terms of modes so that you can plot it as a function of the two modes. So here is the positivity domain of the plus and minus modes. One is in red, the other is in blue. So they are both positive together, only in two squares here, symmetrically. The two squares because we have two ways of choosing the sign of the square root in the beginning, which I mentioned, and my convention will take that square root. Now, interestingly, that's the positivity domain of both the modes together. The elliptic contour here inside it is the positivity of the dissipation of the viscosity factor, A. So as you see, it is not just enough to have positive viscosity factor to have right dissipation, but it's this. So from here, we immediately find out the necessary condition for the stability in the limit and the long wave limit, the hydrodynamic limit. So that's this square. And now if we will consider the conventional isotropic pressure, we see that these are the, so substituting this function into the previous, where is that, previous? The arrows in a different ways. Aha, found one. So into here and plot it. Then you see that the violation of positivity occurs at exactly this value. So there's no surprise that all the, or here, I started with the BGK, but certainly that concerns whatever realization of the lattice Boltzmann. Because I'm talking about the necessary condition, that means for the hydrodynamic equations, which are the same independently of realization. And they will be all predictably violating necessary condition of stability. It's just that value which was found empirically. So that part is fully explained. Oh, that's something which we don't need. Okay, if we go back to the expression of these modes and consider the already specified dissipation condition, we immediately find the following conditions on the pressure: that it must depend on the velocity, that's point one. Moreover, it must depend in such a way that it vanishes at the ends of the admissible interval of velocity at plus minus 1. So at the largest velocity, equal the size of the lattice link. So it vanishes. And also it has to be bounded in slope between 1 and 2. So symmetric like that. Now, this is where we say, this looks like asymptotic freedom. That means interaction, or the interaction parameter, or the coupling parameter, which we associate with the pressure, should depend on the energy scale, or in that case from the velocity, but it depends at the velocity square, of course, and that has to vanish at the largest possible energy. That means velocity equals 1. So that is very similar, that's why we use that notion, to the asymptotic freedom in quantum chromodynamics. Well, as you know, historically, quantum chromodynamics was plagued by very bad divergences for most of its early life. And until in two fascinating papers by Gross and Wilczek and Politzer, using the renormalization group approach, it was shown that the coupling parameter has to depend on the energy scale and has to vanish at the highest, at the infinity. So the interaction should disappear in that sense. So for us, it's very similar because we are considering the sort of renormalization group, cos-graining, and the stability of the fixed point of that, the hydrodynamic stability, is directly leading us to that condition. All right. Now, let's come back, but the condition of stability is actually rather broad. So it does not define the pressure uniquely. So I only define it at the ends of the interval and the slope at the ends. And also there's some inequality for the slope. So it can be between 1 and 2, or minus 1 and minus 2, depending on the end of the interval. But what else can be said? And now let's look back at this expression for the pressure, non-equilibrium pressure tensor, and note that there is a distinguished case, which we'll call renormalizable. Renormalizable here means that if we, in our case, if we can put the compressibility error to 0, if we can cancel it, then we can renormalize the parameter so that beta, so that we get fully Navier-Stokes expression with the renormalized parameter by incorporating the positive dissipation rate, the viscosity rate, A. Okay, so then no error in viscosity terms, so nothing left here, fully renormalized in that sense. So let's see, what does this condition mean? So we have expression for that, which includes the pressure and the derivative of the pressure with respect to velocity itself. We want to put it 0. So what is that? That's ordinary differential equation first order. It has solution 1. And this is this. So you see the 2 times the square root of that velocity, so on. What is that? You guessed it right. If you put it back, this is entropic equilibrium. So pause a bit and think about it. So we have postulated long ago with Santos. So before I postulated the entropy, Alexander was also doing similar work at that time, to mention. And then with Santos, we found this solution. Then Alexander, once again, recently found it in molecular dynamics. So everything somehow goes to that expression. And yet again, we derived it from completely different consideration, from the linear stability analysis, necessary stability condition, and renormalizability. How much time do I have? Oh, enough. So, well, we can quickly look over the checklist of that expression. So it's positive, symmetric, and concave at that. So, and also that the anisotropy associated to the velocity dependence comes at order 4. That means it is detached from the quadratic earlier terms, advection terms in the Navier-Stokes equation. And therefore, well, we knew that from the entropic, that you can use that for simulation in the same level of accuracy as the conventional thing here. As the conventional, I mean, Maxwell equivalent, and that it is asymptotic free. Now we can talk about mechanism of linear stability through two instances. So how the entropic equilibrium in this case deals with the stability, how it averts to bring in the instability into the system. Well, first it's because of the dispersion. So that is the conventional isotropic, which violates now the CFL condition, not the dissipation condition in that plot. That's only the dispersion. Whereas the speed of modes in the entropic, you see it adjusts to stay inside this area where it satisfies automatically the CFL condition up to in both the limits 1 and -1. And this is the plot for the dissipation. So standard and entropic, that one I was already showing, the violation of positivity at the ultimate number 0.42. And the entropic actually does not violate any dissipation inequality. So that is the necessary condition. So we have now a system of 3 variables, so 3 populations, and we can ask further question. Okay, so we have found out something about the stability in the limit of long waves. So k going to 0. So that's hydrodynamics. What about other possibilities that things might be unstable in the through the kinetic modes? So we have one more mode somewhere. We don't see it in the hydrodynamics, but it is in the kinetic equation. So in this case, we can do actually analytically the study of the necessary and sufficient condition for linear stability of the entire system of 3 variables. And that was already not a minor work done by Ali, essentially. So behind it is the notion of sure stability, so that you write a characteristic polynomial with long coefficients, and you have to find the conditions when the roots of these polynomials stay inside the unit cycle in the complex plane. So here is the illustration of a situation when you reasonably small viscosity and already at velocity equals 1. So that's on the border. So that is the roots or root locus of the characteristic polynomial for the conventional isotropic pressure. As you see, some roots are going out of the unit cycle. And here, there's a marginal case U equals 1. So for the entropic, they stay on the unit cycle all the time. So it is also stable. Now, the interesting observation is that the stability condition we found for the hydrodynamics that I mentioned before are the same as for the full system. So the condition at the Knudsen number, that was your question, going to 0, is necessary and sufficient for all Knudsen numbers in this case. So there is no extra conditions of stability for the entire system, which is very interesting after all. So it's not necessarily that it will persist in the higher dimensions. So what about higher dimensions? Well, in higher dimensions to make, well, as I've said, the necessary conditions, they stay. So we can analyze a little bit in more detail. So in 2D, you have two previous normal modes and one shear mode in addition. So shear mode is slower than the other two, and so it does not contribute a new condition, new condition of stability. So the normal modes actually answer the question. So, but unfortunately, the full linear stability analysis analytically would need to solve for the coefficients of the polynomial of order 9, and that's already a little bit too much. So we resorted to the conventional numerical solution of that problem. And as you see, here is the difference. So these are the two conventional, so it's basic K still. So two conventional equilibria. One is the second order polynomial, that's one. And this is the product form, the Maxwell, which I call. So, well, we know that they are all saturated at 0.42. And one is slightly better than the other. So above is the entropic. So as you see, it stays unconditionally stable, so that the domain of stability in terms of velocity is not dependent on the viscosity at all. So you are free. Well, I'm not saying you should simulate it around velocity 1, of course, and there are these terms which are spoiling Galilean invariance are already quite significant. But we can safely simulate in the same region as the others, but without losing any stability. That's about, and here is more detailed plot of directional stability for the wave vector in all the directions. As you see, so there are two lines, one for low viscosity, one for the small viscosity. So entropic again is this, and as you see, it cuts out the full cell of the lattice. So this is one. And the others are the shrinking domain of stability for the polynomial and for the product form. So now this was the linear stability case. And now let me briefly, I still have, I think, some minutes, mention the sufficient conditions or the nonlinear stability. So that is where Santos probably wanted to speak. So I will make a connection to that. So all the conditions I'm talking will become sufficient, so that you have to distinguish between the necessary conditions before and the sufficient conditions now. However, the sufficient conditions, when you come down to the linear stability domain in the lattice Boltzmann, have to turn into the necessary conditions there, which we already established. So there must be a match. Okay, let's see. So the so-called entropic lattice Boltzmann That is to restore the H theorem in the discrete time version. So with the over-relaxation incorporated into that notion. So long sentence, what it means. So we construct a different mirror state. So the propagation stays the same, but now the mirror state around to which this is over-relaxing is found from the entropy condition, and which says that this entropy of the initial state pre-collision should be equal the, so that's the definition of the mirror state, should be equal at the mirror state. Oh. Would draw the picture, yeah, actually. But all right, that's it. Oh, this is, no, that's a little tricky thing, which I don't know how to open. It's not the, yes. All right. So good. Okay, I will quickly draw that. If I still have time. Okay. Good. So it means that if we have the contours of entropy with the equilibrium somewhere in the middle, I'm drawing as a concave body. So because the entropy is convex, so they are surrounding. So we have initial state, and we draw a line through that and find another solution to that. So the solution to this equation, if there are two, one is trivial, alpha equals 0, of course, that's here, and the other non-trivial is here. So, and that can be shown, of course, that since by construction, the entropy, if I take the beta equals close to 1, this is 1, and here is the actual post-collision state, not exceeding the mirror state. Importantly, it's a little exercise, simple but very important, that when this simulation is resolved, and that means the entropy is well approximated by a quadratic form around the equilibrium, then the solution to that equation gives me alpha equals 2. So that means it is matched to the BGK, standard BGK. And since we have already established for that case the stability, the necessary and sufficient condition, then it is matched. All right. So recent work, which I'm saying Santosh is supposed to present, I think, is, why is it so black over there? I don't know. Okay. Is it visible like that? Oh. Okay. Is actually the solution strategies for that entropy estimate, for this equation here, to find alpha. Of course, this is a transcendental equation, so which has to be solved somehow numerically, typically, but some people have developed the more analytical methods of approximating that equation. Here is, I took the picture from the paper by Santosh and his team some time ago about the simulation of some very high Reynolds number flow past airflow. So, but that's not my focus of today. So actually, so finally, oh, still have 15 minutes. So another way, which is called, we call entropic multi-relaxation time method. So I must say before going to the multiple relaxation time, open the next slide. That, you see, from the previous plots I've shown, the work was more thought in terms of how to relax to the equilibrium, with which rate each moment is relaxed. Here, the difference of my viewpoint here is that you have to look at the equilibrium itself, not the way you are relaxing to it. So BGK, in that sense, is absolutely fine once you have the entropic equilibrium there. So it is unconditionally stable linearly, and so on. So, but much work was done to somehow mitigate the absence of unconditional linear stability in the conventional understanding of the equilibrium as a polynomial or as a product form by choosing different rates of the relaxation. Sometimes helps, sometimes not, but as you see, it does not dissolve the question about unconditional stability. So what is the entropy doing here? So this is a very dense slide, but which to say we split the 9 moments, the natural moments. It's an example of moment system for the 9 populations and represent this population in terms of 3 components. So kinematic, shear, and higher order. So here is explicit expression for all the 9 populations. You don't need to remember that. Most probably you know that. So, but, okay. Now, as I said, mirror state is what defines you the model. And here, the rules for the mirror state are the kinematic certainly are not changed. These are conservation laws. The shear moments are doing the BGK. But BGK is doing that on all the moments. Here only is done on the shear moments, on the second order moments. And we have a tail of, so this is the head, this is the neck, and this is the tail. The tail somehow collects all the higher order moments and has a parameter there, so which is the interpolation between the equilibrium of that high order moments and the current state. So formally, for any gamma, this recovers the Navier-Stokes with the same viscosity coefficient. So viscosity does not depend on that higher order moments. And it is okay to think, okay, we don't need to, if gamma is 2, then that's BGK back, right? But nobody said you should do that. So you can do something else. For instance, plausible seems to be to put gamma equal to 1 and just eliminate. That's kind of a regularization, what people call, or equilibration of higher order moments. But when we're talking about equilibration, we can look at some other book of statistical mechanics, or better say the notion of entropy. So, and Professor Dr., this serious guy is Professor Dr. ETH, Professor Dr. Rudolf Clausius, who introduced the notion of entropy, and the notion of entropy in his statement is very famously, energy of the world is constant, entropy of the world tends to a maximum. That's actually a very clean mathematical statement. So you maximize something under the condition of fixed something. In this case, energy, but then now what in our case? And okay, so that's basically for fun. This is Rudolf Clausius, again, a little bit younger. And this is I found it a piece of his presentation on the entropy which was done in Zurich in this year. And this is the statement, which concludes his talk. And this is in German. So, and this was German grammar to it's one sentence. So to get the message, you should not look at the beginning. You have to scroll down and read the final part. And that's the final part, so which is the original German language statement about the maximizing the entropy under the constraint of constant energy. So that's for fun. Because for us, what is a constraint? And what we know what is the entropy, but what is the constraint? And the constraint for us is the over-relaxation, fixed over-relaxation of the second order moments. So that's when I build the mirror state, I do this flipping around the equilibrium state for the second order moments, and that is non-negotiable. That gives me the fixed viscosity. All the rest is in my hands, and so I can plug it into the entropy, ask for the critical point, independence of the parameter gamma, solve it. Well, that's a nasty equation numerically. Not so nasty as the previous one, entropy estimate. This one is much nicer. But still, you even can work it out around the equilibrium state and use it as a formula where you see that there is, the gamma is 1 plus something, which is the ratio of the deviation of the scalar product, special scalar product, which is termed the entropic scalar product of the deviation of the second order moments and normalized by the deviation or the size of the deviation of the high order moments. And as you see, this not necessarily a small correction to 1, can be of same order, and it is actually of same order in most of the cases. So here is, okay, let's keep that slide. That's some graphical illustration. Let's look at the comparison. I'm coming to the conclusion. I still have 5 minutes. That's good. So, what? Why is not running? Running with some delays. Okay. I don't know. Okay. So this is the example. Decaying turbulence for 2 situations. So that's the entropic version, and that's the multi-relaxation entropic. So two schemes, as you may see, they are not just actually same. So this somehow has more smaller features, actually. Well, look by eye. Let's see at the spectrum. So when we take a coarse grid, so that's a coarse grid, and that's the spectrum. So these dots are the entropic lattice Boltzmann, and these lines, 4 different, they are all for 4 different multi-relaxation time modes. So I have shown one, but certainly there are other representations like Martin Geyer's central moments, and also different partitions of the moment system into yellow and red colors I shown. So they are fairly different, quite different models, but on the level of simulation and statistics, they are not distinguished from each other. And you may see that actually the difference is in the smallest, in the shortest eddies, smallest eddies, where actually there is more dissipation in the, so that's hyperviscosity effect, which we will hear from one of the talks later, I think. This, as far as I've seen on the program. Now, this is the coarse simulation. If you, you see there's no LBGK. So if you increase the resolution, then LBGK comes back. It becomes stable. So here it is unstable. And it just, the same effect as the entropic lattice Boltzmann. And these guys, important to what I wanted to show in this flow, that the result is moment indifference. So it doesn't matter what really you are taking in terms of the moment system to represent with natural moments or whatever moments. So result is the same. So I close my talk with some collection of simulations with the multi-relaxation times. So this is already somewhat advanced setting with the grid refinement and all that. So the Reynolds number is not particularly high here, but there's another effect which we want to capture, the transition effect from laminar to turbulent. And mostly I want to show the effect of this stabilizer here. So whenever you see this brownish color, that's 2. That's where we don't have problems in the flow field. That's where simulation is resolved by fact, by the fact. The system still chooses by itself to be BGK. So it likes BGK. So that means there is, I think, some unfairness sometimes in the community towards BGK. BGK is a good model. It is actually one of the best. It's simply that it has to be formulated in the right way. I think. Okay. And so this is some other comparison to experiment or to other simulations. This is a fairly complex engine type geometry where we have a moving piston and the fluid is forming the hollow jet, and then there is a vortex breakup and residual turbulence in that setup. So here is a comparison of mean and RMS velocity profiles at certain angle, crank angle of the piston with both experiment and DNS simulations here, just to show the good comparison. All right, so here is my summary. So my focus today was about the necessary conditions for linear stability. And what we found was surprisingly similar to asymptotic freedom in quantum chromodynamics. Not surprising because we have, after all, a strongly coupled system. So that means there are conditions on the velocities which are not met by the physical velocity. So we are constructing a non-physical system trying to simulate in some limit the true physical system, the Navier-Stokes. But by doing because of numerical super efficiency in the lattice Boltzmann is super efficient. So then we have to think, what do we want? Numerical stability or formally some notion of the isotropy, which is not. So entropic equilibrium was derived in a fairly different way, and it shows unconditional linear stable. And there are other situations, nonlinear stability, that have to be matched to the result limit. I'm done. Thank you very much for your attention.
On the coffee breaks work? So it's supposed to start.
Yeah.
Do you have coffee outside? Or?
Yeah, it's outside in the evening.
Outside. So we probably, since it's relatively short break, we should maybe have 1 or 2 quick questions and then we should move on to coffee break. Because it's,
if I can give the quick answer.
Yeah, quick question. Okay.
Yes, many thanks for your very nice introduction of the PBC. So I have a question. Do you use the Maxwellian equilibrium or the entropic equilibrium in your PBC model?
Yeah.
Which equilibrium is used?
The entropic.
Entropic.
Yeah.
And another question is
In most of the cases, maybe sometimes we use the third order polynomial as an approximation, but the theory says you have to use that because all minimizations and so on, they are around the entropy.
And another question. So if you want to add the force, the body force into the system, I think the mirror state should be modified, but I didn't see that in the paper.
Well, no, you can see it in our paper because look at the entropic formulations for the multi-phase flows there. So of course there is a forcing because of the, well.
You modified the calculation of gamma, not the mirror state.
No, but yeah. Okay, I see. No, but the gamma defines you the mirror state. So there, the force enters the gamma, yes? Yeah. It's not the same. It's not the same as without the force. Yeah, please look at this. I think it was publication in some your physics letters or something like that. Yeah, so the force contributes to that. It does. But the mirror state, you see, mirror state is a very broad notion. So you have to specify. So each time you specify gamma, you specified this given mirror state. And it depends very much. So if you have specified it as a constant, let's say, which is majority of the MRT papers, then, for instance, it's not obvious that you will match even if you are using the entropic equilibrium, that you are not matching the BGK limit somehow. So then you have to go back and analyze again that system for the linear stability. You will be surprised.
So again,